So, good morning, everybody. Once again, this is this is Doug Oldfield, one of the business and sales development, one of the sales and business development managers for Palisade. And today we're going to be looking at risk and its applications, or rather a couple of specific applications in terms of cost estimation and risk registers. So happy New Year to everyone, by the way. I'm guessing there's quite a few people I know on this call already, and it's a new year, so best wishes to everyone. So just a couple of minutes, I'll just talk about, just give you a little bit of an overview about myself, about Palisade, and then we'll a very quick kind of run through of some of the theory of Monte Carlo simulation and why you might want to use it before going into the models. Now, I think this session is scheduled to last an hour. I'll be amazed if I can keep it to an hour, but I will try my best. Sometimes they do overrun a little bit. Just a little bit about myself. I've been with Palisade for the last 7.5 years. I've got a 3-year-old daughter, well, 3.5-year-old daughter, and a 6-week-old son. That's him there. He's a chunky little fellow, but what that means is that I'm a little bit sleep deprived at the moment, and you can probably hear from my voice I'm also fighting off a little bit of a cold, so you have to excuse me if I'm a bit slow on the uptake, or you hear this kind of like heavy breathing or rasping or coughing throughout the course of the presentation. My background is that I originally have a degree in politics and philosophy, which is absolutely no use when it comes to getting a job in the real world, or at least it wasn't for me. So I kind of went through a few different things and ended up at Palisade eventually. So I guess that kind of highlights something which is I think is important to raise, and that's that sometimes people think that you need to have a degree in statistics to understand all of this stuff, and I don't think that's the case at all. And hopefully over the course of the presentation I'll maybe give a little bit of an overview as to why that's not the case. At first, some of the concepts which I'm going to be showing today might come across as a little bit strange if you've not seen them before. I mean, obviously I know there's lots of people on the call who've kind of been using at risk for a while and maybe just want a little bit of a refresher. But for those of you who haven't used at risk, some of the things that we're going to be talking about might seem a little bit strange, but believe me, once you start using the software, once you get to play around with it and start building models with it, it's very, very hard to imagine ever building an Excel model again which doesn't use it. So hopefully we'll give a little bit of a flavour of that over the next hour or so. Palisade itself, just a little bit of a corporate overview. We've been going now since 1984, so a very long time for a software company. And what we make is a number of different software tools which help to basically to understand risks and ultimately to make better decisions. So they kind of fall into the category of decision support tools. Now, we have a lot of users worldwide. We've got users in some very, very different industries, which I'll talk about a little bit more in a moment. And we're taught annually to lots and lots of postgrads, undergrads, academia. We have lots and lots of licenses out there. In fact, later on today, I'm going to go and present to a university MBA course here in London. Along with the software, we also do training and consulting. So some of what you might see, or sometimes clients buy into the idea of quantitative risk analysis as a methodology, but maybe aren't quite so sure about how best to implement it, or want some expert guidance. And so we do a lot of training and consulting, etc., where we really kind of work with clients to help them best understand and implement the tools and methodologies for their own requirements. We also do a lot of custom solutions as well, which is something maybe I'll touch on a little bit towards the end. So in terms of our clients, well, some of our more recognizable client logos are on the screen at the moment. We sell to lots and lots and lots of different industries, pretty much every industry that you can imagine. And the reason for that is that what we sell are some software tools which add extra functionality into Excel. Now, because virtually every company worldwide uses Excel, it means we've got a fairly large potential marketplace, which is obviously great. So I think oil and gas is probably our largest vertical market in terms of annual revenues. Although I'm guessing maybe that might be a little bit impacted upon by the current price of oil. Maybe not. Maybe sometimes we find that when things are going bad in an industry, that's a time when people feel the need to really get into risk analysis in a bigger way. But mining, insurance, pharmaceuticals, government, healthcare, manufacturing, consulting, you name it, we sell to lots and lots and lots of different industries worldwide. And as I think the previous stats said, we supply, I think, 93 of the Fortune 100 companies. So we work with some very large organisations, but also some much smaller organisations too. It's not all kind of big Fortune 100 companies. It's very common for us to sell to small consultancies where there might just be one or two people working there. And what we make, I mean, today is really going to be about at risk. So at risk, I'm going to explain a little bit more about how it works in a little while. But we make a whole set of packages or tools, all of which give different types of capability and functionality within this idea of decision support. From a cost estimation and risk register perspective, at risk is by far the most commonly used. You could make a case for using top rank to do some auditing of models, or maybe decision trees to look at different types of options that are available. But really, at risk is going to be the key focus for today. We do have some regular training courses, so regular webcasts on all of the other tools, etc. And actually, in case you're not aware, and often people aren't, these sessions are all recorded and put on our website, or certainly a lot of them are. So if you go to the Palisade website, which is here, this is the training page, and then go to training and events, and then scroll down a little bit to free webinars, and then when it highlights live webinars and archive webinars, just click on that, and then that takes you to the webcast archive, where we've got like a whole host of previous webcasts that have been given by Palisade staff and also customers as well. And that's the last year and a half or so, 2 years, and then we've got a whole load more in this previous archive. So this is a really good resource if you want to find out more about some of the tools or certain applications in different industries. So do take a look at that if you get the chance, and this session will be recorded and put in there as well. With what we're going to be looking at today then is at risk, and I'm really going to give a very quick run through about what at risk does in Monte Carlo simulation, because often I kind of talk for too long on this and end up not being able to show the software in sufficient detail, which seems the wrong way round. So in the event you do feel as though I haven't covered this in enough detail, do take a look in the webcast archive, or of course email in and ask any questions that you might have that you're not sure about. But a lot of this is going to seem like fairly theoretical text, and I find that the software brings it to life. But just to give you a quick run through of at risk, what at risk does, it uses Monte Carlo simulation, and the idea behind this is that we, instead of living in a static or deterministic world where we can predict the future with extreme accuracy, which of course is a nonsense. What we look to do is we use probability distributions to really try and capture and model uncertainty within Excel or project. And the way that at risk does this is by using these probability distributions to generate many thousands or tens of thousands or hundreds of thousands or even millions of different scenarios to show lots and lots and lots of different kind of combinations of possible events, rather than just seeing one possible worldview or a static or deterministic one. And what we then end up with is the ability to talk about how confident we are in a particular outcome or event occurring. Now, this will become a little bit clearer once I show the software, but that's what the software is doing from a kind of like a theoretical standpoint. And the starting point really is Microsoft Excel. As I said, everyone uses Microsoft Excel, or most people use Excel for any kind of business planning. And how a regular Excel model works is that we start off with these point estimates. So we think about our model, we think about the numbers we want to put in there, and whatever these numbers are, whether they're volume, price, cost, or revenue. Obviously today we're going to be talking largely about costs and risks, but it could be any variable at all. These are then typically constructed to build a big kind of Excel model, sometimes incredibly complex and vast Excel models over multiple worksheets or workbooks with all sorts of functions here, there, and everywhere. But ultimately, the idea of building an Excel model is to really get some kind of metrics from it, and from a project perspective, these might be costs, they might be start date, MPV, and IRR. From oil and gas perspective, it might be the amount of oil in a reservoir. But ultimately, these are typically a single number. So things are distilled down to a single number, and then of course big decisions are made on the back of this. And the quote that I've kind of been using for a few years now in these presentations is this one by an old English statistician from just after World War II, which says that essentially all models are wrong, but some are useful. And this is very, very true. Whenever we build a model, it's wrong. It's as much as we might, our egos might like to tell us otherwise. Models are wrong because the future's outside of our control, and it's impossible to forecast with a degree of accuracy what's going to happen. So the idea really of at risk is to try and make models a little bit less wrong and a little bit more useful. And some of the things that we're trying to overcome is well, there's a few things. So number one, this idea that how can we be confident that our single point estimates are accurate? How are we able to pick one scenario out of a whole universe of possible scenarios for what might happen? How can we capture the relationship between input variables? And of course, this idea that when we build a model, we spend all this time building a model, but typically all of the various errors and assumptions that go into making the model. So the errors around those are typically forgotten about, and the decisions which are made are made without maybe the full understanding of the impact of uncertainty. And so what we're going to see over the next 55 minutes or so, or 50 minutes, is how you can kind of overcome some of those issues with at risk. And really the idea being is that there's, wherever we look, whenever we're talking about Excel models, but there's these probability distributions everywhere. There's distributions for costs, for revenues, for bad weather delays, for durations, for I don't know, delivery dates of children, for journey time to work, for whatever it is. There's uncertainty, and what we're doing with that risk is trying to capture that. And the way in which that works is that we take an Excel model, on an existing one or a new one, we look to find the uncertainty in the model, and then we convert them into probability distributions. You probably hear an airplane going overhead at the moment. At risk then uses these distributions to generate lots and lots and lots of different scenarios, and then we compute the outcome over and over and over again. And then from that, we get to talk in terms of our confidence level. So what at risk does, it allows us to move from this static or deterministic world into a world of uncertainty and probability distributions, and to be able to talk about things in terms of ranges and talk about sensitivities, etc., which I'm going to come on to in a moment. So there's lots of things about at risk in terms of the benefits, and I'm going to be talking about these benefits as we go through, and hopefully they'll become apparent as well. But there's a whole host of reasons why we might want to use at risk, and some very, very important reasons from a business perspective, in terms of what we can do, and also the things which it makes possible, which we can't do without using at risk or Monte Carlo simulation. So enough of the PowerPoint. I'm sorry, I probably spoke a little bit longer on PowerPoint than I intended to, but I think it's now overdue time to take a little look at the software. So what I'm going to do, I'm going to load up at risk, and of course what you'll see, this is version 7, which came out a few months ago. I've actually been demonstrating version 6 for the last few months because I keep forgetting that version 7's there, but I'm finally getting around to showing it. And what you'll see is that at risk, I press the launcher, it's loaded up Excel, and then it's added some functions into the Excel function library that weren't there before. And these are all the at-risk functions. And actually, from a technical perspective, it's what we call true add-in to Excel. You'll see that within the Excel function library, you now have all these at-risk functions grouped. Now, why is that important? Because it allows you to use at-risk with all of the other Excel functions, and it allows you to use all of the other Excel functions with at-risk. So that opens up a very, very flexible, infinitely flexible modeling world with at-risk, where we can use just simple things like drag and drop or copy and paste, through to if statements embedded with at-risk functions, through to min-max, sum ifs, offset indirect. However complex your Excel models are, you can use them in conjunction with at-risk and vice versa. There's certain things which aren't always ideal with at-risk. Anything which needs to be calculated on an iteration by iteration basis, data tables, etc., can slow things down. But actually, once you start using at-risk some more, you'll find that the being able to use at-risk means that you often don't need to use any of those functions. So there's this whole kind of you can start by using at-risk on a very, very simple level, or as you get to know it better and better and better, it opens up more and more possibilities as to what it can do. And of course, I mentioned at the start that we do training courses. This is something that we really recommend, if at all possible. When you start using the software, try and come to a training course. Even if you don't come to a training course when you first start using it, use the software for a few months, and then come along and find out what you hadn't already figured out for yourself. They're really really valuable things to attend. Anyway, let's open up a model. So we're going to be looking at a cost risk model. So what I've got a little simple cost estimation model I'm going to kind of expand on, and then I'm also going to talk about how we go about adding a risk register to this. So this is a very simplistic little model. We've got a project here where we've got 8 different cost elements or line items, and each of them has been given a single point estimate. And finally, we've got a total project cost down here of 18.5 million. So, as I said before, the first thing that we look to do with that risk is to identify what elements in our model are uncertain. And because this is a cost model, and let's assume that we've got no control over these costs. Nothing's been kind of agreed in advance. We just don't know exactly how much they're going to cost. What we're going to say is that there's some uncertainty around how much each of these cost. And so the first thing that sometimes clients do is look to think about things in terms of ranges. So instead of thinking in a single point world, we start to then think, okay, so what's the minimum and the maximum, or maybe what's the minimum, most likely, and maximum value, and just try and understand or get some ideas about what the likely spread of values are for a particular cost. So here we've got a minimum and most likely a maximum, also known as a 3-point estimate, which is a fairly common way of doing things. So the base cost has been given us the most likely, and then we've asked the project manager or the cost estimator or cost engineer, whatever you want to, whoever's developing the model, what the lowest value is and what the highest value is. Now, sometimes people would just add up the sum of the mins and the sum of the maxes and say, okay, this is the worst case scenario. So this is the best case scenario. This is the worst case scenario. But that's not really a very good way to do things. I'll try and be polite, because really, when we talk about 3-point estimates, when we talk about minimums and maximums, what we're saying is that actually these are unlikely events in themselves. We're talking about this is the absolute maximum it's going to be. This is the absolute minimum, but those are unlikely events. So we wouldn't really expect to see a minimum or maximum cost actually being reached on a line item very often. The likelihood of 2 coming in at the same time, or 3 coming in at the same time, the odds just become smaller and smaller and smaller. And so the reality is that if we've characterized our minimums and maximums correctly, then we're never going to see the sum of the minimums or the sum of the maximums. This is just something that we would never ever see. Because the reality is that some are going to be low, some are going to be high, and some are going to be kind of cancel each other out, etc., which I'll show in a little while. So one of the key things about this is that if you are on the contractor side of things, and you submit bids. Sometimes clients would look at maybe their maximum costs, and then they would base their bid around that because they don't necessarily want to end up out of pocket, which of course is something which is very reasonable. But the issue with that is that then typically you would be overbidding, which is all very well if you haven't got much competition, because it means that ultimately you're gonna get more profit on it. But if you're up against competition, you might be pricing yourself out of the running because actually this is an unrealistic number to start off with. So how does at-risk work? How does at-risk kind of overcome these issues? Well, as I said, the first thing that we do is we look to assign probability distributions for each of the uncertain elements. So the way we do this is by clicking Define Distributions, at which point a distribution palette appears. So broadly speaking, there's lots and lots of different types of distributions, and they're split into two different categories. We have our continuous category, or continuous distributions, which is where we have maybe a range of values, and anything along that range is theoretically possible, which is typically what you tend to see for costs. And then the other category is discrete distributions, which is what we would typically use for modeling risk events. So does this event happen? Yes, no. How many times does this risk happen? And I'm going to show kind of both of them throughout the course of the demonstration. Now, the most commonly used ones are grouped together here. You can also set up favorites, which is something that I haven't done because, along with actually using version 7 for the first time, this is a new laptop, so I haven't customized it as I want to. But if we wanted to, I could say, right, well, look, I use PERT distributions all the time. I also use Bernoulli distributions all the time. Let's have those two as two of my favorites. So you can set this up so you don't need to be scratching your head each time you use it about what type of distribution to use. Now, the topic of choosing the right distribution is a fairly in-depth one. And it's certainly one which we haven't got time for today. I can certainly send around a couple of little kind of presentations, but it's something which is really covered quite a lot over the course of the training course. It's fair to say that the vast majority of our customers won't look beyond this common tab here, probably 99.9% or something. But the training courses go into this in quite a lot of detail. But there's also lots of information on the internet. There's information in the software. Wherever you are in at-risk, you'll see this. There's often these little question marks. And so what this does, it opens up a context-sensitive help menu, which is, I've just clicked on one for a triangular distribution, which gives a description, some examples, the statistics behind it, and so on. So you do have some guidance in there, and as I said, there's often a lot of information on the internet as well. And finally, if you've got some historic data, which is something I'll try and cover at the end, you can also use at-risk to run some various tests and tell you what type of distribution best fits your historic data. Okay. For now, I'm just going to use a PERT distribution, and the reason I'm going to use a PERT distribution is because the parameters which describe that distribution, the minimum, most likely, and maximum, are conveniently the same as our 3-point estimate here, where we have a minimum, a most likely, and maximum. So the first thing I'm going to do, I'm going to name my distribution. So what at-risk has got an intelligent naming system, which is pretty good. But on this case, what it's done, it's picked up the value here, land, and then the value of probabilistic cost. So I'm just going to say that I want this just to be the cost of land, just to make it a bit shorter. And the next thing I'm going to do is I'm going to click on this little button here, which is going to allow me to assign Excel cell references as arguments for my distribution. So when I click that and say 1, 2, 3, and I hit the enter button, and what I now have a distribution for my land that has just been built up from those Excel cell references. So in D3 we've got the minimum, excuse me, 1.5 million. In E3 we've got the most likely 2 million, and then in F3 we've got the maximum, which is 2.8 million, and that's what's being shown here. And actually, can I just customize this? So because I haven't really customized, I'll do that later. I was just going to lose some of the decimal places. But what this is now showing, this is showing the spread of possible costs for land. Down here we've got 1.5 million, the minimum. Up here we've got 2.8 million, which is the maximum, and here's 2 million, which is the most likely. So the first thing to say is that the cost of my land is never going to be 1.4 million. It's never going to be 3 million. It's always going to be between these two variables or values, because that's what I've set up. And so at risk isn't magic. It's just like Excel normally. It's dependent on the information that we put it in. And so, of course, people often say garbage in, garbage out, which of course is very, very true. But my argument would be that if someone feels that they're competent or qualified enough to put in a single point estimate for an at-risk model, or sorry, for an Excel model, then surely they should be able to also think about what the kind of the extremes are, what the minimum and maximums are. And so from a very, very simplistic perspective, even if your kind of minimums and maximums are maybe not as accurate as they should be, then compared to using a single point estimate, the results that you're going to get are going to be a lot more meaningful and a lot more valuable from a decision making perspective than if you just use a single point estimate. So if I click on OK, actually let me color the cells as well. You'll now see that in this cell, if we look up at the function bar up here, it's saying that in here we've got a PERT distribution. And when I start tapping the F9 key, you'll see that what we now have is a dynamic value for my cost of land rather than a single point estimate. And so what the software is doing from a technical perspective, it's taking samples from that distribution and it's putting them back into my Excel model. And so now I have this land cost which is uncertain. So I'm simulating uncertainty. So what at risk is doing, it's taking an endless number of samples or scenarios from this distribution and it's putting them back into Excel. So what we're able to see is lots and lots of different scenarios for the cost of land between 1.5 and 2.8 million rather than just having a base cost of 2 million. So what the software is doing is taking samples from here, and it's taking samples that are based on the shape of the distribution, which is a little bit of a funny concept. But when I said before that when we talk about minimums and maximums in particular, these are kind of unlikely events. We wouldn't expect to see the minimums and the maximums. We'd expect to see something from the most likely, and then as we get out towards the maximums, these become less and less likely. And so that's actually what we're seeing here. We have this most likely point, and then as we get out towards the maximums, you can see that the curve gets lower and lower and lower, and so the samples are less likely to come from, say, this point here than this point here, because the curve is lower. And so what we would do, we would call these things the tails. These are the tails, or the extreme events of our distribution. And so the samples are less likely to come from here than here. And actually, if we look up at the top, so these things are called delimiters. So what the delimiters allow us to do is we can just grab them and see how likely it is that the sample is going to come from a particular point or particular range. So for example, if I wanted to find out my P90 for land, so what am I 90% confident that my land is not going to cost more than, and that value would be 2384. So if I wanted to make sure that I'm pretty confident that I've got enough money in my budget for land, then I could choose the P90 or the P80 depending on how we want to do things, and that would be the number maybe that I might input in for that particular cost element on its own. If I wanted to be more conservative, I might choose the P95, in which case I'd put 2469 into the budget for land. If I was a bit more kind of not averse to taking risks and didn't need quite as much kind of confidence, I might choose, let's say, the P75, in which case I'll put in 2224 for land. I'm going to come back to this idea of confidence levels a little bit more when I talk about the outputs from a distribution. But that's what the software is doing. So it's generating samples over and over again and putting them back into Excel. Now, just by way of comparison, if I just show a different type of distribution, or maybe a couple of different types of distributions, if I use a triangular distribution, which is one that people often use when using 3-point estimates, you can see that broadly speaking, the shape of this is very, very similar. You have a slight overestimation of the tails by comparison with a PERT distribution, and a little bit less around the most likely, but you're still very much in the same ballpark as with the PERT distribution. Now, if I use a uniform distribution, say, okay, then you can see that this looks very, very different. So whereas a PERT and a triangle both have a minimum, most likely, and maximum, with a uniform, all we have is two parameters, the minimum and the maximum, and that's what we're seeing here. So it's got the same minimum, 1.5 million. It's got the same maximum, 2.8 million, but then there's no kind of bias towards a particular point. So we have a much larger weighting towards the tails of the distribution here. In fact, the tails is kind of almost a meaningless perspective when we're talking about a uniform distribution. But these areas here are just as likely to happen as this area here. So let me clear the overlays. Okay, so if I now click on OK, and then if I just drag this down, then what you'll see is that I now have a distribution for buildings, for raw materials, for salaries that have also been built up using the minimum, most likely, and maximum. So that's this idea that we can use all the Excel functionality. So I've just kind of dragged and dropped those down. So we've got the same distribution. Now, of course, you don't have to do this. You could have a normal distribution for buildings, or I'm not quite sure why, or a triangular distribution for salaries, or whatever. You can mix and match. But for the sake of convenience and speed, I'm just going to choose the same one for each. Now, down here, if I just add these all up, I've now got a project cost of 18,830. But of course, this is just one scenario. This is one iteration. So if I tap, oops, what am I doing? This new laptop, the control and function buttons are the other way around, and I keep them turned off the screen, etc. So hopefully everyone's still there. So if I just start tapping F9, you'll see that what I'm doing now is I'm generating lots and lots and lots of different scenarios for my total project cost. So what do I want to do with that? Well, project cost is really the thing that I'm particularly interested in. The cost of the individual ones is interesting enough, but what I want to do, I want to find out how much my project is going to cost me. And in fact, the question I want to answer is actually, if I put 18.5 million into my project budget, what chance have I got of, or how confident am I going to be that I'm going to be able to complete this project within my original project budget? So if I'm going to say that I want at risk to give me 10,000 iterations. Interestingly, I've noticed here, this 10,000 always used to be the kind of the maximum pre-filled one. You could always write 1 million iterations if you wanted to, but 10,000 was always the maximum, so or the highest number shown here. So people often assume that 10,000 was the biggest, but you can have as many iterations as you want. Of course, the more iterations, the longer the model takes to run, but I'm just going to run 10,000 because I think that would be more than enough for this particular model. You've got some tools, by the way, in at risk, which allow you to do some convergence testing to make sure that you're basically running the right number of iterations, and you can explore that a little bit more detail if you want to under simulation settings here, and then the convergence tab. But I'm going to just use 10,000, and so when I click start simulation, what you're going to see, so this is, first of all, this is in demonstration mode, so this is running very, 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 very slowly compared to how fast at risk runs normally. But I like to show this because it means I can talk a little bit about what's going on in the background. And so when I click start simulation, at risk has started off on the process of taking 10,000 iterations or samples or scenarios, however you want to call them, from each of my 8 input distributions. So it's then sending those samples back into Excel, and Excel is then adding them all up down here using the same sum function, and that's being used then to drive this histogram here that's being generated by at risk. So if I turn off demo mode, you can see it runs much, much faster. And so what we are now seeing here is, instead of seeing one scenario for my project cost or 3 scenarios, what we're now seeing is 10,000 different scenarios for our project cost. And so down here, this is the best case scenario, a minimum cost of 16,356. In the worst case scenario, 22,787, and absolutely everything in between. So the question I wanted to ask was, so what's the likelihood that we're going to meet our original project budget of 18.5 million? Well, we've got maybe a 26%, let's say a 1 in 4 chance of finishing this particular project within our original project budget. Not too bad, but also not too great either. In the worst case scenario of 22,787. Well, actually, this kind of goes back to what I was saying before about if we just add up, say, all the maximums, then typically when we run a Monte Carlo analysis, what we would see is that the actual value that we come up with is nothing like the one that's in there. And actually, 22787. Well, let's see if we go to 22 million. Oops, I'm typing in the wrong place. Once again, I'll blame the sleep deprivation. There's a less than a 0.5% chance that we're going to be exceed 22 million. So if you were to put this into your project budget and you had some competitors who happen to be using that risk or another Monte Carlo simulation tool or anything, then you're going to come out quite a lot higher than they are. So that's what we're able to do with that risk. In the most simplistic of senses, that's what that risk is doing. We use first of all we identify the uncertainty. We capture that uncertainty using probability distributions. We run a simulation, and then we look to analyse the results. And so this is showing us the best case scenario, the worst case scenario, everything in between, and also how confident we are of a particular value or set of values. So as I said, we talk often about confidence levels and p-values or percentiles when we talk about at risk, and I'll come back to this a little bit later on. But what companies typically do is to set a level of confidence that they're happy with, and then that becomes the company view on reporting project costs or maybe the numbers that get submitted for bid. So instead of picking a single point estimate for each thing, instead we talk about so what we're going to do, we're going to put the P90 cost, that's going to go into our project budget, or the P80 cost is going to go into the project budget. Which is obviously a much more robust and sensible way of doing things than assuming that a single point estimate is remotely correct. Now, from a display perspective, we can change how we see things. We can have a cumulative curve instead, which shows exactly the same information. It's just displayed in a different way, and different people prefer different ways of seeing things. All this information is very, very customizable. You've got lots of different options down here. You can put markers on the graph to show, say, our mean and our P95. We can change the color. We can do all sorts of things with the actual graph. We can take it out. We can put it into Excel. We can take the image. We can manipulate it how we like. We can do lots and lots of things with the actual reporting of this. But ultimately, that's what in the most simple sense, that's what we're doing without risk. But of course. Of course, there's a lot of other things that we can do with it. Now, just before I carry on, let me just double check to see if there's any questions here. I've realised I've been talking for 40 minutes and haven't looked at a single question yet. Thank you for the congratulations on the boy. So, some questions. I would like to use the webinar at a later date to inform other staff within our firm of the benefits of at-risk in our construction cost consultancy. Is it possible for me to rerun the session at a later date? Yes, it is, Mike. I've hit the record button, and for everyone who signed up to the session, there'll be a link to download the recording. I would like to know how to manage running a simulation where input cells are located on different worksheets. But it's at-risk just takes the model structure, so you can have multiple worksheets open, multiple workbooks. It's very, very simple to do that. At-risk just functions like Excel. So as long as the workbook's open or the worksheets aren't are available, then you would just have your functions embedded across all the different worksheets. You don't have to have them all concentrated in one place. So a further question with an email address. If I remember, I will send individual emails out in response to these. But I think what I'll do, I will if I just send round a how do I do this? Let me show the control panel. I'm just going to send everyone my email address here. So in the event that anybody needs anything specific, please send me an email to doldfield@palisade.com. Let's just write that down here in case you don't see it in the chat panel for whatever reason. Oops. Try and spell my own name. Once again, I blame sleep deprivation. Actually, no, that's a blatant lie. My typing is not the most accurate on a good day. So doldfield@palisade.com is my email address. Do ping me an email if you've got any specific questions I don't cover over the course of this presentation. What else is there? Could the confidence parameter be different for each element and be optimized by itself through an outer loop in the simulation? Yeah, for sure. You could so you could have different distributions used. You could have different confidence levels. You could have distributions as parameters. So you could use an uncertain distribution as a input parameter for for another distribution. You can do that. How can probability of occurrence play part in this simulation? Well, I'm going to talk about risk events in a little while. So thus far I'm talking about uncertainty around costs, and I'll explain a little bit about differences in a little while. Could we define a range of distributions for a single uncertain element instead of one single distribution, which we may not be sure about? So if I understand your question correctly, yes, you could. I mean, going back to what I said before, you could have a distributions, so uncertain inputs for your probability distribution. How do I choose what distribution is best for my data? That's the million-dollar question, Winnie. As I said at the beginning, I'll send around some notes on that to anyone who wants it. Please send me an email and then I'll send around the PowerPoints. But you can use historic data. You can look on the internet for information, or better still, come to one of our training courses and learn or understand how the different distributions behave. Because actually, what you'll find is that once you kind of work with that risk and you kind of know a little bit more about the distributions in the first place, it becomes quite straightforward to actually choose the right one. Well, this one's a log normal distribution, or this one we should use a tri-10. It becomes much easier to choose the right distribution once you understand what the distributions actually are. And as I said, there's lots of different types of distributions, but there's frankly, you could probably understand 10 distributions, and that would be absolutely fine to then be able to choose a decent distribution for your model. Can you correlate two variables? Yes, you can. I'm going to come on to that in a short while, and we're going to send a handout after the webinar. What I'll kind of leave that in your hands. The PowerPoint and everything, they're quite heavy, so I don't want to block up people's emails or use their data up if they're downloading onto a handheld or something. So if people want the PowerPoint that I showed at the beginning, please send me an email and let me know, and I'll be happy to ping it across to you. Gosh, there's a lot of questions here. There's quite a lot of people on this session, it's fair to say. Would you explain briefly what's your guide selection distribution? Well, I just kind of covered that slightly, and frankly, we probably haven't got enough time to kind of go into that in more detail. How do I account for correlation? I'm going to talk about that in a little while. Is it possible to define our own distributions and/or mixed distributions? Yeah, you can set up your own distributions. You could for example, you could use risk resample to sample from an existing set of data. You can even draw your own distributions, which I'll come on to in a little while as well if I get time. Someone says all good in Johannesburg. Excellent. I'm pleased. Always good in Johannesburg. Always good in London. So let's go back into the model. I've actually forgotten exactly what I was talking about now, but I'll stop again in another little while to talk about some more questions. It's also occurred to me as well that there's oops, what am I doing? I don't want to be sending. What am I doing? I'm emailing myself. Let's close down Outlook, or you'll see exactly how many reminders I've got to get through. So let's go back into the results. So next up, I was going to talk about the tornado graph. So typically, the next question after we've done this analysis is really to start to find out which factors are the most significant in terms of our model. And so what I'm going to do here is I'm going to use these tornado graphs to really identify which factors are having the most significant impact on my overall model. And so what this is telling me is that the cost of buildings is by far the most significant, or the variability around the cost of buildings is the most significant in my project cost, followed by other general overheads, land, and so on down the list until we get to vehicles, which is really kind of having a fairly negligible impact. So what does this mean? Well, if I just grab this and drag it out, what you'll see is on this scatter plot, this is where our 10,000 scenarios have all been plotted. So along the x-axis, we've got the cost of buildings, which was between 4 and 8.5 million, I think. along the y-axis we've got the total project cost. And so what this scatter plot is doing, it's showing us the relationship between the cost of the input, in this case the cost of buildings, and how much our project costs. So we can see that when the cost of buildings is at the low end of things, so our project cost is low. When the cost of buildings is increased, our total project cost increases, which of course is maybe what we'd expect, but it's still nice to be able to see the relationship between the variables, and also because it's not then just a black box where you kind of don't necessarily know what's going on between the relationship between things. You've got the correlation coefficients are shown here, and you can do all kind of types of analysis with this if you particularly wanted to look at this a little bit further. So this is showing us that relationship. Whereas if I go down the list and look at vehicles, then really you can see it's all over the place. It doesn't matter if vehicles are high or low, the project cost is not really dependent in any meaningful way on the cost of my individual vehicles. So this tornado graph is a way of being able to show which factors are the most significant. And what the numbers are actually showing us, these 18.04 and 20.725, etc. Excuse me. This is showing us what the average cost of buildings is when the average project cost is when the buildings is at the P10 and when the buildings is at the P90 on the other side of things. Okay, so maybe a slightly quicker view on sensitivity analysis than I'd like, but it was as we're a little bit pushed for time, I probably shouldn't talk for too long about any one thing in detail. So next up, someone mentioned correlations in one of the questions, and so this is this idea that in real life, and when I talk about real life, I mean kind of real life outside of an Excel model, so the thing that we're actually trying to build a model about, there's often a relationship between two or more input variables. So for example, if you're looking at a demand model, if you're in a shop, if you put your prices up, then demand typically goes in the opposite direction, so you have an inverse relationship between price and demand typically. For construction and cost estimates, let's say you've got the cost of steel is an input, and the cost of steel pipes is another input. Well, then there's going to be a relationship between those two, and so there's often a relationship between input variables, and so it's incredibly important to make sure that those are captured within our model, because the whole point of using at-risk is to make our models realistic. And so if there's relationships that exist in real life, then we should put those in our model, and it's important to do that, because otherwise what we would typically be doing is underestimating the tails, because when things are correlated, they move in the same direction, so if or in the opposite direction, but when we're on a simulation, if we don't put those correlations in, then we mean that sometimes things can cancel each other out. Sometimes something could be low when the other thing is high, and that's not how things work in reality. So let me just talk about that a little bit more. So if I click define correlations, then what I'm going to do, I'm going to say that I want there to be a relationship between, let's say, land and buildings. And so here what I do, I get to say whether my correlation is positive or negative. So that the example I just gave of price and demand, that would typically look something like that, because somewhere along this axis anyway, between no relationship whatsoever and a kind of like a perfect negative relationship. Land and materials, I'm going to say that I want there to be a fairly strong correlation. Now, some people would kind of say, how do you know what correlation coefficient to choose? And there's a few different answers I'll give to that. Number one is that if you have any historic data, you could use the correl function in Excel to derive the correlation coefficient, and you could just type it in here, and then you have your correlation from your historic data that's then applied to your new data going forward. If you don't have any historic data, and often there isn't any, because often different projects have got different costs, different inputs, etc., then you could think about things in terms of bands, or so you might have, for example, 0.2 is a mild correlation, 0.4 is a medium correlation, 0.6 is a strong correlation, and so on, and just kind of have that kind of grouping. and a lot of companies do that. And actually, for people who get worried about, well, how do I know if it's a 0.42 or 0.44 correlation? You can actually use at risk to do some testing to find out what the difference is of a correlation. And actually, there's something called a risk sim table. So, well, first of all, what I'm going to do, I'm going to let me say that I want my correlation to be 0.4. And so if I click on OK, put the matrix down here. Okay, so this is my correlation matrix. And so what you'll see is that land and buildings have now got a little bit extra function added to them, which is this risk core map, which is short for risk correlation matrix. And so what we're seeing here is that we now have this correlation between land and buildings. And so, but what we could actually do, I don't normally talk about sim tables when I talk about a cost model, but we could use a very, very nifty little at-risk function called a risk sim table, which is a wonderful function that all too few people know about, unfortunately, when they use at-risk. And so what I'm going to do, I want to analyze basically what the difference would be between a 0.4, 0.6 and a 0.8 correlation. So this is this idea of doing some sensitivity analysis on the actual correlation weighting to find out what difference it's going to make if we have a 0.4, 0.6 or a 0.8 correlation. And so this is a really, really useful tool. It's something called a risk sim table. So if you go to insert functions and then special, and then click risk sim table, then what I'm going to do, I'm going to set up a table of values. And so my table of values here is going to be 0.4, 0.6 and 0.8. So if I excuse me. Okay, so the idea here is that what we're going to do, instead of running one simulation, which is the kind of the usual, what I'm going to do, I'm actually going to run 3 simulations of at risk. Simulation number one, so, and the reason I'm doing this is because of this risk sim table function, which I can use to basically draw in a different value for each simulation. So it's this idea that in this cell we have this risk sim table, which is looking at this table of values here. Simulation number 1, it's going to bring in the first value, which is going to mean that I have a correlation coefficient of 0.4. Simulation 2, it's going to bring in the second value, which is going to mean that my correlation is 0.6. And simulation 3, it's going to be 0.8. The reason being is that I want to see how much difference it's going to make having a different correlation value. This is a really, really, really useful function at risk. You can use this in all sorts of models, not just for correlation coefficients, which is probably quite an uncommon use, but for basically looking to see what would happen if one or more inputs to the model were changed. So risk sim table, look it up if you don't already know about it, and start using it. It's brilliant. So what I'm going to do now, I'm going to run 3 simulations. So if I click start simulation, let me just pause this. Okay, so you can see that what's going on here is that at-risk is running 3 simulations. So now I'm in the second simulation. And so what you'll see is that this value for my correlation is now 0.6 instead of 0.4. If I let this run a little bit more, and now it's 0.8. So it's what at-risk is doing, it's taking a different value for my correlation for each of the simulations. So ultimately, if I now go to my results, this is simulation number 1, simulation number 2, simulation number 3. So how much difference is that correlation coefficient making to my model? Well, in this particular case, the answer is virtually none from a practical perspective. Of course, you might kind of get hung up on this 1% difference, but believe me, 1% difference is very, very negligible when you're talking about probabilistic modeling. And so what we're seeing is that there's a slightly higher chance that we're going to finish under budget if that correlation is 0.6, and a slightly higher chance still if it's 0.8. But really, it's not that much. As I said to you, what you tend to see is that you tend to see more impact around the tails, and actually you'll see that these tails have increased slightly, and this tail has increased slightly as well. But for that particular input, there's very, very little difference. So that's correlation matrices, and that's also the risk sim table as well, which I'm glad I got to show, because often I don't. But the at-risk sim table, it's a really great tool for being able to show what happens if one or more of your inputs change across a distribution, simulation. And actually, let's lose my correlation matrix, because I don't really Neither. Okay, and let's lose these as well. Keep it all neat and tidy. Okay, so where was I? Correlations I've just done. Okay, so next up, well, I don't know if you remember, when we looked at the tornado, we found that the key driver was our the cost of buildings. And so the next thing we might want to do is to think about, this is what I call the brown stuff hits the fan analysis, which is also known as stress analysis from an actual perspective. And the idea of the stress analysis is to see what happens if one or more of our inputs to our model are at the high or low end of things. Now, with a cost model, we would typically look to find out what happens if one or more of our costs is high, because actually if our costs are low, then that's really a nice problem to have. So what I'm going to do, I'm going to look at buildings. And the way stress analysis works is that it allows us to, oops, what am I doing? I'm in the wrong place, that's why. What the stress analysis allows us to do is to run 2 simulations instead of 1, and to just look at a small subsection of a distribution. Now, what does that mean in actual English? Well, when at risk runs a simulation, the samples are getting taken from everywhere in this distribution, from here, from here, from here, from here, from here, from here, and so on. And so that's going to be my baseline analysis, my baseline scenario. But when we look at the stress scenario, what we really want to do is to look at what would happen if maybe one of the tails were the most likely scenario. And so when I run a stress analysis for buildings, what I'm going to do, I'm going to look at what happens when the cost of my buildings is at the high end of things, so between the 90th and the 100th percentile. So at risk is going to run 2 simulations when I run a stress analysis. Simulation number 1 is going to sample from everywhere. Simulation number 2, it's going to basically pretend that anything to the left of this delimiter doesn't exist, and that the minimum cost for my buildings is going to be 6,532, the maximum is going to be 8.5, and all of my samples are going to get taken from this little area here, this little area which I'm placing under stress. So now, if I go down here and set this up, so what I want to do, I want to look at the cost of buildings, I want to stress the high values, I want to look between the 90th and the 100th percentile, and then I click Analyze, and then at risk is running those 2 simulations back to back instead of 1. So simulation number 1 is our baseline scenario, which looks like this, where we've got a 26% chance of finishing our project under budget. If the cost of buildings is at the high end of things, then actually that doesn't look quite such a rosy picture, and actually we've got essentially 0% chance of finishing our project within our original budget if the cost of buildings is at the high end of things. And obviously the curves have jumped across to the right, and suddenly this becomes a more expensive project on the face of things. So this is just something which really feeds into that into the decision-making process. It's, as we say, it's a decision support tool, and so this then allows companies to think in terms of how much effort they want to put into controlling a particular risk, or uncertainty. We've identified that buildings is the most significant. If the cost of buildings is at the high end of things, this is what it looks like. Is that acceptable, or do we want to maybe make sure maybe we speak to legal a little bit more and tie down the contracts a bit more, or alternatively look for an alternative plot, or do something in order to control or mitigate against this risk as best as we can. So that's the stress analysis. Now, you'll have to excuse me for 1 minute, just a very quick call of nature. So I'm just gonna pause for a second, but I'll be back in about a minute or less. Hold on a moment. There we go. Almost fell into my chair, and yes, I did wash my hands before anybody asks. So that was the stress analysis. Let me just have a little gulp of water as well. Okay. So obviously you'll see up here there's lots and lots of different buttons which I haven't touched on yet, but not all these things are probably relevant to a costing model. So I just want to kind of talk about a few other things which I think are quite relevant. So you'll hear exactly how wheezy and out of breath I am thanks to this thanks to this cold, which I think my daughter's given me. First of all, Excel reports. Here, obviously, at risk is about building great models, but it's also about them being able to share those with other people. And so, within here, we have some options in terms of what type of reports that we have. So we've got lots of different ones in here. We can create our own ones if we want. But if I just show you a quick report, then what the software is just doing, it's just bringing out some information about the different things. Got lots of output cells down here, but so what this has done, it's shown me the histogram, the S-curve, the tornadoes. It's showing me simulation information, statistics, etc. And if we wanted to, we could of course just put this in a PDF or a PowerPoint presentation instead. But you've got lots of these different reports all kind of built into here, and you can set up your custom ones as well. But okay, so really, thus far, I've been talking about cost risk and uncertainty around the cost. Actually, let me just have a quick look to see if there's any questions in here before I carry on. Cost estimation without direct correlation may introduce forecast errors. I've just kind of covered that. How can I edit the label of a curve? I run simulation and realised some typos. Simulation takes 1 hour of MS project. You should be able to just do that from the browse results window. So if, for example, you're in browse results, you just change it to whatever you want to. So you can just edit the actual results window if you need to change it. Where's my question panel gone? I've just lost my questions. Hold on a second. I don't know if it's my Q&A. So I'm obviously something of a novice with WebEx or GoToMeeting rather. So I've just lost my question panel. Well, hopefully it'll pop up. Maybe someone can ask me another question and maybe it'll come back up. So just a test question at some point will be. Aha, there we go. Thank you very much. Could the stress function be applied using a discrete set of rare events? Interesting. I'm not sure. I would need to find out. I'm saying, could you send me an email on that, and I'll look into that. I've never set up stress analysis with a discrete distribution before, but send me an email and I'll do that. I could probably sit down and think about it, but then we'll be here a little bit longer. So yeah, send me an email and I'll look into that. Okay. So thus far, I've been talking about cost, the uncertainty around about cost, and it's important actually. The name at risk obviously implies it's all about risk analysis, but from a technical perspective, what we're doing is we're looking to quantify uncertainty, and when we're looking at a cost model, there's some uncertainty in that, and the word risk is a very is very kind of relative or determined. It's determined by whereabouts you're sitting on the fence. If you're maybe the contractor who's buying things, then it's a risk, but if you're a supplier, then it's an opportunity. So what we're really doing is we're quantifying uncertainty, and so there's some uncertainty around the cost of each of these 8 different cost elements. And that's what we've quantified so far. Now, there is, of course, another category of things which can have an impact on the overall project budget. But these aren't costs in the traditional sense. These are what we would term to be risk elements. And these risk elements may or may not happen. So we know when we do this project that we need to budget for all of these 8 things, and then there's some uncertainty around how much they cost. But then there's also some different risks which can typically face any particular project. And so that's what I've got down here. So what we've done with the project managers sat down with a risk manager. They've identified that there's 4 different risks which could face this particular project: so earthquake, bad weather delays, worker strike, and terrorist attack. So when we talk about risk registers, what we would typically, let me backtrack a little bit. So obviously, I'm very aware that some companies would just say, right, okay, well, what we're going to do, we're going to add on 10% contingency for risk. So 10% of the project budget, we're going to add that on for risks, and that'll be fine. And which is a fairly common way to do things. But also, it doesn't seem the most rigorous, well thought out, scientific basis for doing anything like that, just to add a random 10% on. So the idea of a risk register is really or quantitative risk register is to try and figure out exactly how much contingency we should be adding for risk, and how likely it is that particular risks are going to occur. And so risk registers really have 2 components, 2 dimensions. So the first is, if a risk occurs, how much is it going to cost me? What's the severity going to be? How much is it going to hurt? And typically, there's some uncertainty around this. You have an earthquake could be a number 1 on the Richter scale, it could be number 10 on the Richter scale, and the impact is going to be very, very different. Bad weather delays, might last shorter or longer, or whatever. So there's some uncertainty around how much a risk is typically going to cost you if it happens. And so for each of these, I've already built in some distributions. So for earthquake, we've got a log normal distribution. For bad weather delays, we've got a PERT distribution. For worker strike, we've got a triangular distribution. No particular reason other than just to highlight the fact that we can have different types of distributions used within at risk. So there's some uncertainty around each of these risk events. Sorry. Function button in the wrong place, or not the wrong place. It's in the right place for this laptop, but a different place to my old laptop. So when I'm tapping F9, you'll see that this, the severity is changing. Now, what some companies would do when they talk about quantitative risk analysis would be to then take the second component of a risk register, which is the likelihood, or the probability of occurrence, or sometimes the frequency of occurrence. And they would multiply that by the risk amount, and then add them all up and say, right, what we're going to do, we're going to have 1,000, in this case 1,057,000 into the project budget. That's what we're going to add for risk, because what we're doing here is we're taking the average of the severity and the impact, and then we're adding that all up. But of course, this way isn't really the most sensible way either, and I kind of try and be polite about these things, but really, it makes no sense to do things like that, and I'll give a couple of reasons why it makes no sense, and then we'll kind of talk about how you do about it without risk instead. The first is that if this risk event occurs, if there's an earthquake, and for this particular iteration, let's assume there's no uncertainty here. Let's just assume that the earthquake's going to cost 5 million if an earthquake happens. Then surely this number here should either be 0 or 5 million, because if the earthquake doesn't happen, then there's no impact. There's 0. If it does happen, it's 5 million. At no point, nowhere whatsoever, is there 500. This 500. This is like this average number it doesn't exist anywhere. It's either going to be 5 million or it's going to be 0. It's not going to be 500. So this is all kind of very well if you've got a very large number of large portfolio of identical projects where all your risks are the same, and of course then eventually you are across the portfolio, then the average risk is going to be 500,000. But on a project by project basis, and of course most projects are different from the next project and from the next project, it's either going to be 5 million or nothing. And so I'm going to show you how we can actually catch that using that risk. The other is that actually if we look here, so we add up the average risk for earthquake, bad weather delays, worker strike, terrorist attack, and we put 1,057,000 into the pot for contingency for risk. Well, if an earthquake happens, if a worker strike happens, if a terrorist attack happens, then actually, well, we haven't got enough money. We haven't got enough money to pay for them, because we've just got this average, and that doesn't cover any of these. So this number down here is utterly arbitrary and utterly useless in terms of actually quantifying anything in a meaningful sense. So how do we do this without risk? Well, I kind of gave a clue to it back then, and that's the idea that what we're going to do without risk is to build in a conditional relationship so that if a risk occurs, it gets counted in full. If it doesn't occur, it doesn't get counted at all. So this is the idea here that either it's going to be 5 million or it's going to be 0. And so how we do this is through the use of discrete distributions. And so what I'm going to do, excuse me, I'm going to use one of the favourites that I set up here, a Bernoulli distribution, to simulate whether or not these events are happening or not. So if I click here, Bernoulli, then first of all, this is the most common discrete distribution which everyone is aware of. Is if you flipped a coin in the air and you called heads or tails, then you have a 50% chance of heads and you have a 50% chance of tails. So you've got two different outcomes. In the sense of at risk, our two outcomes are a 0 or 1. We have this kind of binary notation. Either it happens or it doesn't happen. So how many times are we going to get an earthquake? Either we get them 0 or we get it once. Now this is showing me a 50% chance of an earthquake, a 50% chance of no earthquake, which seems a particularly risky place to be living or doing any kind of project, unless your project is to analyse the likelihood or impact of earthquakes, I suppose. But if I assign an Excel cell reference, I'm going to say that my probability is 10%, which still seems pretty high. So once every 10 years, we're going to get an earthquake in this particular region. And once again, I'm going to name it. I'm going to say this is earthquake. And so now here what we have an earthquake which has got a 10% probability of occurring within the time horizon of our project. So in 9 times out of 10, there's no earthquake. 1 time out of 10, there is an earthquake. And so now, if I start tapping the F9 key, remembering to press my function button, you'll see that at-risk is generating a stream of 1s and 0s. So I'm seeing actually more 1s than I'd expect, but that's just what happens sometimes when you're doing random sampling. Sometimes you get a large number of results where you think, oh, that's surely not random. But actually, I haven't had a 1 for ages now, and of course now I want 1 and I'm not getting 1. Here we go. Sooner or later, I'm going to get a 1. There we go. So on this particular iteration, my risk has occurred. So my earthquake has happened. And so what I'm going to do, as I said, what I want to be able to do is to make sure that things either happen or they don't. They get counted in full, they don't happen at all. So first thing I'm going to do, I'm going to edit this and say that this cell here is now equal to the severity multiplied by this simulated occurrence. So this simulated severity multiplied by the simulated occurrence. So for this particular iteration, my earthquake hasn't occurred, and so there's no value here. You'd think, like Pavlov's dogs, that sooner or later I would learn that my function button is in a different place, but I don't. So there we go. Now I've simulated that the earthquake has occurred, and this gets counted in full. So it's either gets counted in full or it doesn't get counted at all, which is perfectly logical. I think it's exactly how we should be doing things. If I just drag these down, let's just give each of these the same one. Incidentally, if we have an event which can happen on more than one occasion, then we could use something like a Poisson or a discrete distribution to simulate something which can happen on multiple events or multiple times. But because I'm already 15 minutes overdue, I'm not going to kind of show that at the moment. But yeah, you could use a Poisson distribution or something. So next up, I'm just going to say that I want this to be a risk make input. So what I'm doing here, I'm just literally kind of treating, at-risk has got the ability to combine 2 or more input distributions and treat them as a single input. And so what I'm doing here is I'm just doing that with the combination of severity and likelihood, because otherwise when we do a tornado diagram, what you'll see is that the things that occur at the top of the tornado diagram are always the occurrence. So whether or not the event actually occurs, always up at the top of the tornado. But what we really want to be able to do is to see which risk elements are kind of should be up at the top of the tornado instead. So I've just changed that, and so it's a risk making. But we could also use a risk compound function as well, which is something else that you can use to when you're modelling risk events. So let's now run a simulation. So here what we have is a stochastic risk register. So instead of adding 10% contingency on for risk, now we can see what the kind of the spread of values are. So actually, just like before, we can drag the delimiters. I mean, actually, in the worst case scenario, we've got 23,287 in terms of risk, which is actually pretty much the same as the maximum project budget. But this is a pretty unlikely event, so we can once again, it's about confidence levels. So some companies might choose a P90, in which case the P90 we'd add for risk would be 3,284. P20 would be 1,645. If you wanted to be ultra conservative and say P99.5, then you put in 11,469 for risk. But you've now got the the transparency and the ability to see exactly how confident you are at any, with a given level of contingency within the project budget, which is a great way of seeing things. And of course, now what we can do, when we look at the results, here's my project cost before any risks were added. And here's what it looks like after they're added. So you can kind of see that because you've got this long tail, it's kind of compresses the graphic here. But you can see that we've got a very different picture. So from having a 26% chance of finishing within our budget, that drops to a 15% chance of finishing within our budget. The P10 is very different without risks to that with risks. And so our project budget is changed accordingly. Now, finally, just to kind of wrap up with this, what we can then do with that risk is we can then use that risk to tell us how much what kind of amount we need to put into our project bid or our project budget or allocate for risk at a given level of confidence. And the way we can do this is through the use of some at-risk statistics functions. So what we have here are, so at-risk contains a number of these different statistics functions, which basically are a way of getting information from within these kind of results graphs, etc., and from the simulation, and putting them back into our model. And so what I'm doing here, so I'm looking at cell L4. So you can see up here, if I talk about this, so cell L4 is the total budget. And so what this particular function is telling me to do is saying, okay, so what we want to do, we want to find out at a given percentile, given confidence level, what is the project cost going to be? And so we can see that if we want to be 75% confident that we have allocated enough money within this project budget to cover risk events and the uncertainty around the costs, then the amount we would put into the budget is 2875. If you wanted to be more confident that you've got enough money within the budget, if you want to feel more secure, kind of warmer, happy, fuzzy feeling that doesn't keep you awake at night wondering if you've got enough money in your project budget, then you might choose a P90, in which case you would put 22,749,000 into the project budget. If you want to be more conservative still, then you might choose a P95, in which case this would be the amount that you put into the project budget, 24.76 million. Then we've got a little calculation which is actually saying how much contingency do we really need to add from the base case cost in order to cover both risk events and also cost uncertainty in this particular case. And so if we want to be 75% confident, then actually we'd need to add on an 11% from our base case value of 18.5 million. If we want to be 90% confident, then we'd add on 4249, which is 19% contingency. And if we want to be 95% confident, then we'd need to add 25% contingency. And of course, it doesn't matter what you choose. That's kind of very much down to the individual company. But what this does, it feeds into the decision-making process. So the analyst can say to the manager, or the manager can say to the shareholder, how confident do we want to be, first of all, that we've got enough, that we're submitting the project here? How confident do we want to be that we're not going to end up getting stung by this? And okay, we want to be 95% confident. In that case, we need to add on 25% contingency for risk events and uncertainty. Now, another way, something else which some people do as well is that sometimes, and I apologise to any project managers amongst you, sometimes project managers aren't trusted that you know, this kind of, if you add on contingency for risk, then it's going to mysteriously disappear within the project budget because costs escalate and they're not controlled in the same way. And so sometimes what happens is that maybe the decision is that, okay, so the project manager, this is what they're given as their project budget. They're given the P75 or the P80 or whatever it is, and that's their project budget. But then what we're also going to do, we're going to put in maybe the difference between the P95 and the P75, let's say 3.8 million. What we're going to do, we're going to put this into a management reserve fund. And this is something which is there if it's needed, but the project manager has to justify exactly why they're going to be drawing down this reserve fund. This isn't just for, you know, bad management of the project. This is for like a real kind of unforeseen event or whatever, or you know, the project manager needs to justify why they're able to draw down this money from the management reserve. So that's kind of, well, I've pretty much come to the end of what I wanted to talk about. So that's at risk for cost risk analysis. I can just hear a baby crying in the background now. That's at risk for cost risk analysis. Incidentally, my wife is looking after the baby. I haven't just left them in a cot in a room on their own. So that's cost risk analysis, that's risk registers, and that's at risk. So let me just double check if there's any more questions. Can at risk be connected to other products of Palisade? Yeah, for sure. All the products work together. So at risk, you could have as inputs for big picture. You could have Evolver and at risk, Precision Tree and at risk. All the tools kind of work together. I'll stay on just in case there's any other questions, but if there are no other questions, please feel free to go about your normal lives, your normal business. Thank you all very much for your time today. Hopefully you enjoyed the session. Hopefully my kind of wheezing and rasping didn't put you off too much, and hopefully you kind of saw the value of at risk. It's a wonderful tool to use, and obviously if you've got any questions at all, please send me an email. The link to the recording will be sent round. If you want me to send you the PowerPoint I used at the start or anything else, please just send me an email and let me know. So thank you all very much for your time. It doesn't seem that there's any more questions. Oh, someone just said, how do you combine the risk part to the normal graph? Well, actually, that's pretty straightforward, Brad. I just added this here is just a sum function, so it's just H12 plus H20. So I've just made an integrated cost and risk model where I added the risk amount here to this amount here and set it as a risk input. So it's basically all kind of combined together rather than treating them separately, which is of course something which is also something which is really valuable as well. The two should be treated together rather than separately because there's uncertainty around both. Okay, great stuff. Thank you all very much, everybody, and I hope you enjoy the rest of your days, weeks, years, and so on.